Right, 2016 higher level, question 5, U values, on page 51 of your books, and it's the last one we're going to do before we wrap up the topic. The reason I wanted to do this one is because it's a timber frame wall and there's one or two potential areas of confusion with this question. I'm just going to look at the makeup of the wall first before we actually read the question. We have a timber frame wall. We have the internal leaf is a timber frame panel with your plasterboard on the inside, insulation, and your OSB wood on the inside, and the cavity, and then your concrete wall with some plaster on the front of that. What can be confusing about this is if you were to take a U value through this area, you're going through the plasterboard, the insulation, and the OSB wood or the plywood. The breather membrane and the air tightness layer do not come into consideration here. If you were to go through this area here, you're bringing the wood into place, into consideration. So there's, as we know, there's timber studs going up throughout this, and there's a timber framework in this panel, and that adds more to the calculation. The reality is when you're doing a U value calculation for a timber frame panel, you have to do it for here and through the wood. Now, doing that calculation is kind of a level above leave insert. If and when a timber frame question comes up, they always put a little note in here. The timber studs of the inner leaf need not be considered for your calculations, so we don't have to worry about including the wood and the insulation. We just include the insulation. And as I said, the air tightness layer and the breather membrane also don't have an effect on the U value, so we don't include those. So read the question first. The external wall of a house of timber frame construction has the following specifications. There's all the parts of the wall, there's all the sizes. Thermal data for the outer leaf and cavity. So the outer leaf will be the block part and the cavity is the gap in the middle. Thermal data for the inner leaf, that's the thermal data for the timber frame panel. And as we said there, the timber studs of the inner leaf need not be considered. Part A, as always, calculate the U value of the wall. Part B, calculate the heat loss, the cost of heat loss through that part of the wall with all your information. That's the usual. And part C is how much insulation needs to be added on. So again, once you can understand the makeup of the wall and how to lay it out, it's a fairly straightforward calculation. So we'll go through that there now. First of all, as I always say, these are your formula that you need to know. They're not in log tables. You can't look those up in the exam. You must know those off the top of your head, so make sure you understand those. That's a makeup of the wall, so a little sketch of the wall that we're dealing with. We have external render, external block, a cavity, OSB wood, insulation, your timber stud, that's the wood. I've written it down just to have it there, but again, we know that doesn't have to come into it, and your plasterboard. Alright, so we've got 6 layers to put into our table, and added to that we must have the invisible external layer and the invisible internal layer, which must go onto it as well. Take that out. That's the table of information of what we were given in the question. I always say it again, do this in pencil, just in case you have to correct any mistakes. If it's in pen, it can get very, very messy, so do it in pencil. And element, conductivity, resistivity, thickness, resistance, all of that, you should be able to just write that down off the top of your head as well. That needs to be learnt off. You need to be able to draw that table up without thinking, essentially. R equals T over K, and R equals R by T, just in case you forget those. Elements or layers, you can call it either. External surface, external render, concrete block, cavity, OSB, insulation, plasterboard, and internal surface. The question gives us the full resistance of the internal surface. It gives us the full resistance of the full resistance of the internal surface, and the full resistance of the cavity as well. So we just need to calculate this 1, 2, 3, 4, 5 of them. It gave us resistivity for the external render, and it gave us conductivity for the rest of the part, so just make sure you put those numbers in the right places. And the sizes: 19mm 0.019, 100mm 0.100, 18mm 0.018, 120mm 0.120. This one could catch you. It's 12.5mm that's given in the question, 0.0125. So at this point we can just take our calculator out and start working through those calculations. First one then, so we're going to do or by t, so we have 2.170 multiplied by 0.019, so 2.170 multiplied by 0.019, that is 0.041. We'll stick to 3 decimal points when we're going through these. Now we have the other formula, t over k, so it's t divided by k, 0.100 divided by 1.320, that equals 0.075. Next we have 0.018 divided by 0.130, that's 0.138. Next we have 0.120 divided by 0.040, that gives us 3. That seems like quite a high number, but again it's insulation, so insulation will have a high resistance. It should end up with a high number. And 0.0125 divided by 0.160 equals 0.078. Alright, so at this point we just go and we add up all of these total resistances to get our full resistance of the wall. So 0.048 plus 0.041 plus 0.075 plus 0.170 plus 0.138 plus 3 plus 0.078 plus 0.104, and that gives a total resistance of 3.654. So from here we do our usual U value 1 over RT, T standing for total, so that's 1 over 3.654. So we'll go 1 divided by 3.654, and that gives us 0.273. That is watts per meter squared Kelvin. We'll stick to 3 decimal places on that as well. It seems to be going better for us when comparing to the marking schemes. That's part A done. So you can move then on to part B. So like I said, an easy calculation once you just get an understanding that the timber stud does not come into play on that. Next we'll go on to part B. Part B is, we'll just take it out and have a quick look. Calculate the cost of heat loss annually through the wall using the following data. So the area of the external wall is 150 meters squared. Sometimes they give you the length and width and you must multiply it out yourself. The average internal temperature, average external temperature, we're going to need to take 6 away from 18. U value of the wall as calculated above, which we've just got. Heating period, 8 hours per day, every day for 38 weeks per annum. Annum meaning year. 96 cents per litre, and the other 2 bits of information we'll need shortly as well. So it's just a case of going through those 5 steps as carefully as we can to make sure we get all our numbers right. If you want to write down all those headings of what you're doing, you can, but the reality is you don't have to do that. All you have to do is write down the numbers to get your marks. So the first thing you have to do is get the U value multiplied by the area multiplied by the temperature difference. That works out. So step 1, 0.273 multiplied by 150 multiplied by 12. That's the U value, which we calculated in part A. That's the area given in the question, and that's the temperature difference. That is 18 minus 6, 18 being the internal temperature, 6 being the external temperature. So we'll multiply those out. So 0.273 multiplied by 150 multiplied by 12. That's 491.4. Now, part 2, you must calculate the time that's on. So I'm going to write down the numbers first and go through them. It was 38 multiplied by 7 by 8 by 60 by 60. Again, if you want to write down what you're doing there, you can, but just the numbers are fine. 38 is the weeks per year that it's on, given in the question. 7 days a week, it says in the question it's on every day. We usually just assume that. Just watch out in case they tell you something different. 8 hours per day, given in the question. 60 minutes in an hour and 60 seconds in a minute. As common sense, we add those in. So once we get that down, we just multiply it out. 38 multiplied by 7 multiplied by 8 multiplied by 60 multiplied by 60. 7660800. 7660800. That's the amount of seconds that heating is on throughout the year in that house. Part 3, it's just a case of multiplying this multiplied by this and divide by 1,000. Again, if you want to write it down what you're doing, you can, but it doesn't have to be written down. 491.4 multiplied by 7660800, all divided by 1,000. So we'll multiply that first, get your answer, and then divide by 1,000, just to avoid confusion on the calculator. 491.4 multiplied by 7660800 equals that. Sometimes with your scientific calculators, it might give you a number to the power of -3 or 4 or 10 or whatever. If that causes confusion, don't worry about it. Just straight away divide it by 1,000 anyway, and I should give you a full answer. 3764 517.12. That's our answer for part 3. Part 4, all we have to do is get that number now and divide it by the calorific value. The calorific value of oil in this question is 37350. So we get 3764517.12 divided by 37350. So on our calculator, 3764517.12 divided by 37350, and that will give us 100.7902843373. At this point, we'll just go to 2 decimal places, so we'll go for 100.79. And then our final step, that's the amount of litres basically. So now we need to multiply the amount of litres by the price of the oil. The price can vary throughout the time of the year. In this case, it's 96 cents per litre, so it's 100.79 multiplied by 0.96, so the 96 cent goes down to 0.96. Calculator then, 100.79 multiplied by 0.96, and that gives us a cost of €96.75. That's your final answer for part B. Now, moving on to part C. I'll have a quick read of it. It is proposed to upgrade the thermal properties of the above wall to meet the passive house standard by fixing expanded polystyrene to the external surface. Given the thermal conductivity of the expanded polystyrene is 0.037, calculate the thickness of expanded polystyrene required to achieve a U value of 0.15. Again, simply put, they want to retrofit that wall and add on some insulation to try and reach passive house standards. Even though the U value actually wasn't too bad on that wall, they want to go lower again to reach passive house standards. So we'll start working our way through that question. We'll go through all the steps that are usually involved. Current U value. Equals 0.273. That we calculated in the first part of the question. So the current resistance is, you can do 1 over 0.273, or you could just step back and you can see our full resistance was here, 3.654. If you were to put 1 over that, you would get 3.654. The required U value so they want us to get from 0.273 down to 0.15. So that means the required resistance that we have to get to find that out, we put 1 over 0.15 and so 1 divided by 0.15, that would be 6.666. Again, you can just load of 6s there, 3 is plenty. So we need to get from this resistance up to this resistance. So we need to take this away from this to find out how much more resistance is needed. So 6.666 minus 3.654. 6.666 minus 3.654, that's 3.012. So essentially the insulation that we add onto this wall needs to amount to a resistance of 3.012. So we'll do our usual working backwards thing from part A. Element, conductivity, resistivity, thickness, resistance, and the element is insulation. The conductivity is in the question. The insulation that we're using is expanded polystyrene. It's got a conductivity of 0.037. Resistivity is not given. It won't be needed. If ever we do need that resistivity, as we know, it's R equals 1 over K. Thickness we're trying to find out, and the resistance we want to get to, this insulation must have a resistance of 3.012. So we'll use our TKR triangle. If I want to find the thickness, it's K by R. If I want to find the conductivity, it's T over K. If I want to find the resistivity, it is T over K, or T over R I said earlier. Anyway, we're looking for thickness, so it's K multiplied by R. That's K and that's R. So essentially we have to just go 0.037 multiplied by 3.012. 0.037 multiplied by 3.012, and that gives us an answer of 0.1114. Okay, you can just, that's in meters by the way, so 1114, we can just round that up to 112 millimeters. Again, if you write down anywhere from, I'd say 110 to 113, you're going to get your full marks there, but we'll just say 112 to get that rounded up to a proper mark. Alright, well done.